So this, now you have understood, students, how this
Yes, ma'am.
scattering of particles by gold foil. Okay. So this was a very important observation that he made. And what does this tell us? Now let us analyze the results that we have got. Now, first of all, he selected the gold foil because he wanted a thin layer, as thin layer as possible. So this gold foil was about 1,000 atoms thick. Okay, and alpha particles are doubly charged helium ions since they have a mass of 4 units. So they're having 4 units because they're having 2 protons and 2 neutrons. So the mass of a proton and neutron, they're equal. So they're having a mass of 4 units. The fast moving alpha particles, they have a considerable amount of energy. So this is another point. So that is why he selected the alpha particles because of that is they have considerable amount of energy, and they are again doubly charged helium ions. They have a positive charge. So they are, as we discussed, fast moving alpha particles. Then what we would have expected, it is normally expected that alpha particles would be deflected by the subatomic particles in the gold atoms. See, if you're taking the structure proposed by Thomson, what Thomson said, he said that it is like a sphere, and the sphere is having lot of electrons present. And this, so if it is really a sphere, as Thomson said, let us put it. So you are having a sphere. Okay, this sphere is positively charged. So it is positive. It is a proton. He said that the proton is a sphere and we are having electrons present. Now, suppose the alpha particles hits the sphere. So alpha particles are positively charged. It is hitting again positively charged. So what would is expected? So one is positive, another is positive, and he normally what we'll expect, as soon as it comes and hits a positive charge, it will get deflected back. So thus it was expected that alpha particles would be deflected by the subatomic particles in the gold atoms, if you are looking at the structure of Thomson. Because the alpha particles are much heavier than the protons, he did not expect to see large deflection. So he expected it to be deflected to some extent, because this is positively charged, this is positively charged. And he thought that alpha particles are very heavy, so the deflections will not be much. There will not be a large deflection because these are much heavier. So it is very difficult for us to deflect a heavy particle. So this is what he was expecting. Now, but the alpha particle scattering experiment gave totally unexpected results. The following observations were made. So what did we see? We saw most of the fast moving alpha particles, they pass straight through the gold foil. So isn't it? We saw in that picture, most of them are going straight, if you see. And some of the alpha particles were deflected by the foil by small angles. Some we saw it was around 30, some particles of one or two particles were 60. So they're deflected by small angles. Surprisingly, one out of every 1,200, that is 12,000 particles, appeared to rebound. So some of them, you can see one in 12,000 particles, they went straight, and you had them rebounding back. That is 180 degrees. We saw that they came back. So that was one out of every 12,000 particles. Okay, so now what does this tell us? So in the words of Rutherford, he said that this result was almost as incredible as if you fire a 15-inch shell at a piece of tissue paper. It comes back and hits you. So if you are firing a 15-inch shell at a piece of tissue paper, it is coming back and hitting you. So since according to Rutherford, it is a sphere, positively charged sphere. So when the protons are going and hitting it, because the protons are heavy, they're fast moving, he expected them to be deflected to some extent. He didn't expect them to come back and hit you. That 180 he didn't expect. Now, what I mean, we can try to understand this experiment this way. So let us imagine a child standing in front of a wall with his eyes closed, or even like, we stand in front of a wall with his eyes closed, and he goes on throwing stones on the wall. So every time he throws a stone and the stone hits the wall, he will hear a sound. So let us say every time he is throwing, or like, every time he knows there is a wall, so he's closing his eyes and he's throwing a stone. He will hear a sound, isn't it? So every time that stone hits the wall, there is a sound. He knows, oh, it has hit the wall. Now, suppose the child closes his eyes and throws stones on a barbed wire fence. So barbed wire fence means we know that that fence will not be compact. So you will have like this barbed wire means we'll have, suppose there is a wall, there'll be like this, there'll be like this, like there'll be some like this, there'll be a, so this is a fence, and it will have something like this, some small, um, there will be a gap, and then here it will be sort of, basically it will be just like, you can imagine them as lines present, and here there are gaps. So this is a gap, this is a gap. Now what he will do, he will close his eyes and he will throw stones on this fence. So what will happen when he's closing his eyes and throwing, most of the time it will go through this gap, because lot of gaps are there. The stone will go through the gap, he will not hear a sound. But sometimes what will happen is it will go and hit this wall, this wire, that wire that is present, that thick wire, it will go and hit sometimes. Then he will hear a sound. But most of the time he will not hear a sound, isn't it? Even if we take a stone and we hit a fence where there are a lot of gap, sometimes we will hit the that wire. So most of the time it will go through the gap, depending on how much of gap is present. So when it hits the fence, a sound will be heard, but most of the time, sound will not be heard most of the time because of the gap in the fence. Isn't it, students? If we were to do this experiment, so all of you, yeah. So when there is a gap, it is not going to hit. So similarly, what we see is here, he saw that. So seeing that previous discussion's reasoning, Rutherford concluded from the alpha particle scattering experiment that most of the space inside the atom is empty, because most of the alpha particles pass through the gold foil without getting deflected. So like the fence, space in the fence, he said that there is space inside the atom, and that space is empty, and through this space we are seeing that the alpha particles are passing through without getting deflected. Now very few particles were deflected from their path, indicating that the positive charge of an atom occupies very little space. So it is saying he saw that only very few particles were deflected from their path, indicating that the positive charge of an atom occupies very little space. And a very small fraction of alpha particles were deflected by 180 degrees, indicating that all the positive charge and the mass of a gold atom were concentrated in a very small volume within the atom. So what did he say? A very small fraction of alpha particles were deflected by 180 degrees. So they went and they came back like a bullet. They went and they came back, indicating that all the positive charge and mass of the gold atom were concentrated in a very small volume within the atom. So students, did you like understand? At least did you get a, I mean, did you get the sort of the, some extent, did you get the logic behind this reasoning? Yes or no? It's a very, I mean, it is not very easy for us to understand. It takes some time. So what we can say that is here, like now if you go back here, so see these, so what does this indicate? Alpha particles, they're going, so there is an empty space. So most of them are just going straight. So that shows that within the atom, There is lot of space within the atom. Then we are seeing that sometimes some of these when the alpha particles, positive rays, they are going, when they are going, what happens is maybe they are they're touching the tip. So touching the tip of that, maybe the nucleus, maybe. Okay, so then they're getting deflected. Then they're going, and some of them are going and hitting the nucleus, let us say. So, or they're going and hitting they're hitting a center, for just to understand. So when they're hitting the center, they're coming up, when they're in the center, he proposed that the protons and neutrons, the whole mass is present in the center. So when it is going and hitting the center, what is happening is, it is coming back. When these rays are going and hitting the center, they are getting deflected back. So that means in the center, the whole mass of the atom is present. So at that time, he said that the alpha particles were going, meeting a charge which is same as their own, and they are getting deflected. So that means to say that the atom is having a lot of empty space, and all its that is the mass is concentrated in a very small region, very narrow region. And this narrow region contains the that is the mass, which is made up of the that is positive charge, and this positive charge is occupying a very small space. Okay, he did not consider the electrons at all, because they have a charge, but they are the mass is very less, one, and these are all fast moving particles, double charge particles, so they just pass through. Unless and until they meet something of their own charge, there is no there is no deflection. Okay, so this was he reasoned down from this experiment. Okay, so here you can see it is going to the, when it is going to the hitting the center, it is getting deflected. Here you can see it is not very, it is almost, it is close, then there is one deviation. Then here you can see, then when see it is going straight, then here it is again sort of coming back. So like this, here it is going here, and then it is getting deflected back. So whenever it is coming near the nucleus, depending on where it is, I would say when it is coming towards the something in the center, a particular region where there is a positive charge present, if it is hitting, depending on how it is hitting, we are seeing that either it is the rays are coming back or it is getting deflected.
And
Okay. Yes.
if alpha particles touches the electrons, what happens, ma'am?
See, nothing will happen, because the electrons, no, they don't have any mass. We saw that it is 1/2000 time. No, so it is negligible. And these are all, see, it is having two protons, and they're going fast. They are doubly charged helium ions, and they have sent purposely. They are sent at a high speed, so that when it comes to electron, it will just knock off the electron. See, we discussed, no, electrons can be peeled away. So this electron will not, it will not be able to deflect the alpha particle. Okay, so that is why it is like here, it is just going straight.
Okay, ma'am.
Okay. Or as you said, no, or I mean, we have to, if you think, I mean, as for discussion, maybe if it is hitting directly an electron, its charge will get reduced slightly, because it will get neutralized. But that the alpha particles, they are fast moving and they are doubly charged, so they are able to just pass through. Okay, students.
Okay, ma'am.
Okay, so this is what he um, Rutherford. That is what he reasoned out. So, and he saw that one out of every 12,000 particles appear to rebound. So that is why he said that it is like as if it is coming and hitting you. One out of 12,000. So this we can try to understand with this experiment. Like suppose it is, we are standing in front of a wall and we are throwing stones. what happens? The wall, the stone, when the stone hits the wall, we hear a sound. But if there is a fence, there is a wall which is made up of, say, iron, that usually you have that barbed fence present, or wooden, let us say, fence present, wall present with lot of gap. Then only some stones will hit the that this one. It will hit the wall. Most of them will go through that gap. Okay, so it is like that. So the rays are able to pass through the gaps present within the atom. So that is why he said that most of the space inside the atom is empty, because most of the alpha particles pass through the gold foil without getting deflected. Then very few particles were deflected from their path, indicating that the positive charge of the atom occupies very little space. Because alpha particle is positive, when it meets a positive particle, it gets deflected. A very small fraction of the alpha particles were deflected by 180 degrees, indicating that all the positive charge and the mass of the atom were concentrated in a very small volume within the atom. Only some of them were actually able to go and hit that the region where this positive charge, where the mass of the atom was present. Okay. Now, this Rutherford's model, there are certain drawbacks. I mean, he was able to explain that no, the positive charge and mass is present in a narrow region. It occupies a small volume in the atom, and there is lot of space in the atom. He was able to explain, but one drawback is there. Now, the drawback is regarding the electrons. See, the revolution of the electron in a circular orbit is not expected to be stable. So, if the electrons are going around in a circular orbit, then after some time it will lose the energy, and then they will get attracted to the positive charge that is present in the let us say in the atom. So any particle in a circular orbit will undergo acceleration. During acceleration, these charged particles would radiate energy. So once they radiate energy, thus the revolving electron would lose the energy and finally fall into the nucleus. So they'll be revolving. After that, they will lose that particular energy, and then they'll fall into the nucleus. So if it were to fall into the nucleus, the atom should be highly unstable, isn't it? Then every atom should be positively charged, because this electrons are all falling into they're losing the energy, falling into the center. They get attracted to the positive charge, and finally, what happens? The atom will be highly unstable, and hence matter would not exist in the form that we know. So if everything is unstable, then if you see, matter always is stable, isn't it? If it is a pen, whatever it is, unless, for example, that experiment that we discussed, that is, if you're taking a comb and combing a dry hair, or taking a glass rod and rubbing it with silk, you're doing some action. Then you see that either the comb gets charged or the glass rod gets charged. So, but otherwise they're stable. Glass rod is stable, then comb is stable. There is no charge on it. So, if it is like if the Ford's model, if we follow the model, according to his model, what would happen? Matter would exist in a very unstable form, and it is not the form that we see. We know that atoms are quite stable. We know that they are very stable. They are quite very, like in case of a solid, we saw they are the most stable. They just vibrate. There is only that vibrational energy. In liquids, we see that there is again some more movement, kinetic energy. And gases, you see that there are random movement. So on the whole, you can say that atoms are quite stable. So this model was not able to explain the revolution of the electron, the presence of the electron, how it is present, that it was not able to explain. But it was able to explain that the positive charge and the mass is present in the center. Second, it was able to explain that there's lot of gap, there is lot of empty space within an atom. Okay, students.
Yes, ma'am.
So this is actually, yeah, this is a an experiment which was like, what they use the word path breaking. So it it helped, Thomson's model. So it disproved Thomson's model. So this model was like that, as we discussed, either a Christmas pudding or like a roti with all, some dry fruits within it. And he said the whole atom is a proton and with electrons present, and so that the charge becomes equal. So that is been disproved by Rutherford. But Thomson said that the charge of proton and electron, they are equal. So here he went to the next level. He said where it is present, where this protons and the mass is present in an atom. Okay, students, any doubts? No doubts. Okay. Now, who will tell me about the that is Thomson's model of structure of an atom? Who wants to attempt? See, it is, again, I always tell you that it's a learning experience. We're all learning. So we will make mistakes when you're learning new things. So that is fine. But you have to make an attempt. So who will make an attempt? Okay. And now I'll start with who discovered electrons, students?
Thomson, ma'am.
Very good, Thomson. Uh, who discovered protons?
E. Goldstein.
Goldstein. Very good. He discovered a proton. And what is the charge of a proton?
Positive, ma'am.
Positive charge.
Positive. Positive,
Very
ma'am.
good. It's a positive. It is having a positive charge. Electron is having a
Negative
Negative.
charge, ma'am. Negative charge. Negative charge.
yeah. So both of the, if they are taking a 1 unit of this, is the charge is equal. Proton and neutron, they're equal in charge. Proton is positive. Electron is very good. Then what is the mass of a proton equal to in terms of the mass of an electron?
2000 times the electron, ma'am.
Very good. So a proton is 2000 times that of the mass of an electron. The mass is 2000 times. And we are taking proton mass to be equal to how much? This proton's mass is equal to, we are taking it as equal to be 1 unit. So we consider proton's mass to be equal to 1 unit. So electron's mass will be 1 by 2000 times the mass of a proton, isn't it? So though electron has the same charge as the proton, its mass, it is very small. We can say its mass is so much lesser than that of the that is the electron's mass is so much lesser than the proton that we consider it to be negligible. We say that the mass of an electron is negligible. So now the scientists wanted to understand how are the electrons and protons arranged in an atom. So they wanted to know the structure of an atom. So many scientists, see, we saw only two. Next class we'll see Bohr's model. Like each one, no, they were able to explain like better. They were like one Thomson's model was there. After that, Rutherford's model. Then Rutherford's model's drawback, Bohr, he explained. He did experiments and he was able to explain the model. First attempt was made by Thomson. So Thomson, what did he consider the that is how did he consider the this one to be an atom to be? So we can consider so we can say Christmas pudding, or we can even consider it to be like a
Watermelon.
like I yeah, we can take an example of our roti. So he said this proton, full proton is one Christmas pudding or roti, and he said in this these electrons are present. Why he said this is, no, the proton is having 2000 times the mass of a electron, so it is big. It is occupying a lot of space according to him, and these electrons are present like this, and the total charge of the electrons, so these are all negative charge, so this negative charge is equal to the negative or the positive charge of the proton. So thus he says this atom is stable. So this was Thomson's model. Okay, so when he said that, then Goldstein wanted to see, oh, is this experiment, like, he wanted to see if whatever Thomson proposed, is it true? or like, is it correct, or is there a change? He just wanted to, he did experiments trying to understand Thomson's experiment. So what he did, he took a thin gold foil, and this has number of atoms. So this gold foil is having number of atoms. He took very thin gold foil because a number of it will have a particular number of atoms, and at the same time it is very thin. Okay. And what he did, then he took alpha particle, that is helium atom, where the electrons have been removed. So helium atom, when the electrons are removed, they have a positive charge. So it is called as an alpha particle. Alpha particle. He passed this. He made this alpha particles hit the gold foil at a high speed. So if it is really a positive charge as proposed by Thomson, so the positive charge, they'll all get deflected. See, positive charge, when a positive charge hits another positive charge, it will get deflected. So according to the Thomson's model, all of them should get deflected. But he saw that they are not getting deflected. Most of them are going through. Like this, they are going through. And then he proposed that is because it is not a sphere. Protons are not really a sphere, uh, and only some places it is getting deflected. So in some places it is getting deflected. So he said the protons are not, the whole atom is not made up of a proton, but proton is present in some region. Some, in a narrow region it is present, because most of the times these rays are getting deflected. That means lot of space is there. They're just passing through. Most of the time they're just passing through. But sometimes what is happening, they're getting deflected. Sometimes they're coming back. And he saw also one out of some 12,000, they're coming back. So that means that positive charge that is present is occupying a small volume. And when this alpha particles hits that particular region, it comes back. It gets rebound. Okay, so that means to say, if you are having positive charge, so according to him, positive charge is present. According to Rutherford, it is present somewhere, very small region. And when this alpha particle hits, it is coming back. Now, if it is hitting somewhere here, it will get deflected. So like that, depending on where it is, or it's very close, based on that, there is, either deflection. Otherwise, they're all going straight. This is what he observed. So he said that the positive charge and the mass of an atom is occupying a small region, which we now know is in the center. We call it as a nucleus. But he was not able to explain this electrons. See, he was not able to explain how the electrons are present. So if the electrons are present somewhere here, these electrons, after some time, they'll be moving, but after some time, they lose the energy. Suppose they're moving around the nucleus, after some time, they lose energy and they should fall off. So that he was not able to explain. But he was able to say that, yes, there is space, a lot of empty space in the atom. Yes, the positive charge in the mass is present in a narrow region. So he was able to disprove Thomson's model, which said that the whole sphere is the proton. He was able to disprove. Okay, students, now is it clear to a greater extent?
Yeah.
Any doubts?
No, ma'am.
Very good. So all of you, it is clear to all of you, right?
Yes, ma'am.
Okay. Okay. So this is again a very important experiment, important finding. Now next class we'll see how this particular drawback about this electron, only about electron he was not able to explain. That again Bohr did a number of experiments. He did experiments to get now whatever the present structure of the atom, how electrons are present in the atom. So so next class we will look into the experiments done by Bohr and understand how electrons are present. Now we know they're revolving around the nucleus. So more about electrons and how it is present within the atom, we'll take it in the next class. Okay, students.
Ma'am,
So, yes.
how are the alpha particles go into 180-degree angle and come back?
So these alpha particles, no, they are actually only the proton. That is, it is a positively charged particle. So some see when he is passing number of rays. Some of the rays, some one or two rays, that it will go and hit the nucleus. It is going and hitting somewhere in the center. It is hitting, like, example is like a this wall, you're having a wired wall. So some stone will go and hit the wire. No, some stones will go and hit the tip of the wire. Some will go and hit the center of the wire. So if it hits the center of the wire, you will hear a sound. So like that, some one or two rays, they are able to go and hit the center of the region where this proton is present. So when it is able to hit the center, it is coming back, because this is positive charge, this is also positive charge. Proton is positive charge, alpha is positive charge. So positive, positive, then it will go, then it cannot go further, it will come back. Okay, so it is coming back because it is hitting something, so that is not allowing the alpha particle to go further, that ray to go further. And this he saw that it is happening 1 in 12,000 times, not always. Similar to our experiment with a child, closing the eyes and hitting the wire, like so many times the child will throw one stone, will go and hit and produce a like a maximum sound. Some will just touch. Most of them will fall through the space within that wire, that iron fence, no, it will like that. So it is going, so it is a positive charge, it's meeting a positive charge, so it is coming back with the same it is going at 180 degrees. So it is returning back with 180 degrees. Okay, so this is again, I mean, all this as such, the structure of atom, the I mean, it is a very I mean, it is little difficult for us to understand, but it is fine, as we go on reading, it will become clear to all of us. So with this, students, so thank you all. So all of you have a great day. See you all on Wednesday. Bye.